Hi, my name is Pravir Sharan, and in this video, I will be telling you how projectile motion works. In this video, you will learn three things. 1. You will understand what projectile motion is. 2. You will prove the formula for projectile motion. 3. You will be able to optimize projectile motion. The definition of projectile motion is a form of motion in which an object or particle is thrown near the Earth's surface and it moves along a curved path under the action of gravity only. So what this means is that projectile motion is like any other motion, except that the force is acting as gravity, which causes the ball to go down in the shape of a parabola. To prove this, let's first start off with saying that A is equal to dv over dt. First, A is equal to acceleration. Basically, the acceleration usually, which is 9.8 meters per second squared, or 32 feet per second squared. Then the t is time in dt and the v is velocity. So what we're basically saying here is that acceleration is the derivative of velocity with respect to time. So multiplying both sides by dt gives us a times dt is equal to dv. Now we can integrate both sides from 0 to t to arrive at something much more convenient for this formula and get rid of the dt and dv. Now on the left side, we found out that the integral of that is at, but since it's a definite integral, we need to plug in t and 0. And on the right side, the integral of dv is simply just v. So, and then you put it from nt and then 0. Now the left side would just simply be a times t minus a times 0 when we plug the variables in. And the right side would be vt minus v naught. Vt is the velocity at time t and v naught is the velocity at time 0, which is the initial velocity. Simplifying the left side of the equation, we get at. And now we can add both sides of the equation by v naught to arrive at the equation that vt, or final velocity, is equal to acceleration times time plus initial velocity, or v naught. This equation will be very important in proving the projectile motion equations. So for a second here, let's try to take a moment out and look at what the graph would look like if we graphed what the ball would go, where the ball would go when it would be launched. So the brown parabola on this graph right here is the movement of the ball, and as we can see, we have the initial angle right there, and we have the initial velocity, v naught. Now we have the y component, and we also have the x component, acting in the x direction. And at this point, we have the max point, which means this is where the ball will be at its highest. Now, if we treat this as a triangle, we can see that this leg is v naught times sine theta due to trigonometry, since it's opposite divided by hypotenuse for theta, and thus other leg is v naught times cosine theta, since it's adjacent divided by hypotenuse. So we can now see that vy naught is equal to v naught times sine theta, and vx naught is equal to v naught times cosine theta. Now we can plug this into our old equation that we proved before, that vt is equal to at plus v naught. But now we can see what v naught is in terms of our y component. So vt is now equal to at plus v naught times sine theta. And this is acting in the y direction, so it would really be vty. And this is all to do with the height of the ball, acting in the y direction. Now, if we take a tangent line at this point here, which should look something a little like that, then we can see that the slope of this tangent line is equal to 0, meaning that the derivative of this graph at that point is equal to 0, and the derivative is equal to vt. So vt is equal to 0. So now we can plug this back in. 0 is equal to acceleration times time plus initial velocity times sine theta. Now, if we move the initial velocity times sine theta to the other side and then divide by acceleration, then we can see that the time when the max point occurs is at negative v naught sine theta divided by a. Now, if we look up here, we know how long it's going to take for the ball to go halfway. But we want to know how long it's going to take for the ball to go from when it launches to when it lands. And this would be twice the distance as the small t, as you can see here. And we'll call this new thing a big T, which is the time it will take for the ball to land again. So big T is equal to 2 times little t, which is equal to negative 2 v naught sine theta divided by a. Now, we know that there is a formula which says that distance is equal to time times velocity. Now, we know what time is, and in order to figure out velocity, we can just realize that velocity is equal to v naught times cosine theta. So, and therefore, the distance is equal to negative 2 v naught sine theta divided by a times v naught cosine theta. And this can be simplified to negative 2 v naught squared times sine theta times cosine theta divided by a. This is equal to negative v naught squared times sine 2 theta, because we have 2 sine theta cosine theta, which can be simplified to sine 2 theta. And this is divided by a. But since a is acting in the opposite force of gravity, this is equal to negative g, and the negatives cancel out, which means that the distance traveled by the ball is equal to v naught squared sine 2 theta divided by g. This is the formula for the distance that will be traveled by the ball when given initial velocity and initial angle. Now, we're going to use the formula from before. The distance is equal to initial velocity squared times sine 2 theta divided by g. Now, we want to maximize the distance that the ball travels. But we want to do it by figuring out what value the theta would make dB the biggest. For example, if theta were 0, then d would be 0. So that would not work, but we have to figure out the value that theta is in order for d to be at its highest point. So if we take the derivative of this, we can see that the derivative is v naught squared divided by g times cosine 2 theta times 2. Now, the v naught squared divided by g is a constant in this case since we don't care about these variables, and the 2 is the result from the chain rule from the 2 theta in sine 2 theta. And if d prime is equal to 0, then we know that d will be at its max. So we have to figure out what value theta is in order to make d prime 0. So since everything else is just constants, all we care about is cosine 2 theta, because if cosine 2 theta is equal to 0, everything else is equal to 0. So setting cosine 2 theta equal to 0, we can see that 2 theta has to be equal to pi over 2, since cosine of pi over 2 is equal to 0. This can also be written as 90 degrees. Dividing both sides by 2, we get that theta is equal to pi over 4, or it can be 45 degrees. At pi over 4 or 45 degrees, the distance will be at its maximum. I did an experiment to test the formula for projectile motion. The distance is equal to v naught squared times sine theta times cosine theta times 2 divided by g. I used a graph paper in the background, gridded, so when I launched the ball, I could see with the footage of a 400 frames per second high-speed camera how far the ball had gone in 4 frames. Then I would calibrate that with real-world measurements like millimeters, centimeters, and meters. Then I figured out the initial velocity and the initial angle from this. Then I predicted the distance that the ball would travel and compared that with the actual distance the ball traveled. This picture was taken at t is equal to 0 frames, and this picture was taken at t is equal to 4 frames. These are the results of the experiment that I did. On the left side, you can see that at t is equal to 0 frames, the ball was at position 262 pixels in the x direction and 215 pixels in the y direction. I used Microsoft Paint to figure out these pixel values. And t is equal to 4 frames, which is 0.0075 seconds later, x pixels was 307 and y pixels was 150. The delta x pixels, which means it changed in the x direction 45 and it changed in the y direction 65. Now, for the calibration, we figure out how many pixels these actually are in the real world. So, at the 0-inch mark, it said 140 pixels. At the 20-inch mark, it said 703 pixels. And at the 0-inch mark, for y, it said 118, and for the 12-inch mark, it said 450. So therefore, in the x calibration, in 563 pixels, that was 50.8 centimeters, meaning 1 pixel was 0.902309 millimeters. And for the y calibration, the in 332 pixels, it was 30.48 centimeters, which means that 1 pixel is about 0.918072. So the average is 1 pixel is equal to 0.910190 millimeters. So the distance that the ball traveled was 79.05694 in pixels, but in millimeters it was 71.95689. So this means that the velocity, the initial velocity, is 9.59 meters per second. The angle in degrees was also 55.3 degrees, and the angle in radians was 0.965. So putting these into the equation, I got a predicted distance of 8.791681 meters, and the actual distance the ball traveled was 8.5368345. So this means that the error percentage was a very small 2.898746. Therefore, I proved that the projectile motion formula works.